Hello, everyone, and happy Friday. Today is June 26th, and this is episode 13 of our Google Hangouts and podcasts and all things DOCSIS. I'm Brady Volp, founder of the Volp firm and Nimble This. With me again is John Downey, DOCSIS guru and consulting network engineer at Cisco Systems. Hey, John, how you doing?
Good. Glad to be here.
Yeah, I'm glad you're here too.
Pleasure as always.
Just before we got started, you were having some networking issues, so we'll see how you hold in there.
I'm blaming on the heat. It's been, I think, 100 degrees every day here in Raleigh.
Yeah, it's 93 down here in Atlanta, so
nice.
It's not bad. Better than a cold. So today we're going to be talking about the trip I had a couple weeks ago to the Angacom show. It was held in Cologne, Germany. And then we'll talk about some topics around optimizing cable modem transmit and receive levels, both to improve DOCSIS service and also help prepare for things like higher order modulations that folks may one day be seeing in the not too distant future with DOCSIS 3.1. Anything else you want to cover, John?
No. Well, you know how it is. We'll just hit it as we go. I'm sure we'll go on tangents and all that.
Yeah, we may not get to any of these topics before we're done. So, I mean, this is our 13th show. We've been doing one a month, so we're going on to our second year here.
Wow. Yeah.
It's going quick. So Angacom was at Angacom last year, or 2 weeks ago, and a lot of our viewers actually attend the Angacom show. So I did run into a number of people who watch these Hangouts. But for those of you who are not familiar with Angacom, it's the European equivalent, as close as you can get to SCTE's Cable Tech Expo, which is our yearly cable convention, so to speak. It's held every year in May or June in Cologne, Germany. If you're German, that's Cologne, Germany, or as close as I can say it. And there's typically about 20,000 attendees at this show. This year, there's about 4,000 vendor attendees. So they have booths and stuff like they do at the Cable Tech Expo, and 17,000 operator attendees. So it's a pretty well attended show. And you have the normal vendors that are setting up booths and displaying equipment, showing the latest technology. DOCSIS 3.1, of course, was pretty big, pretty hot, and there was active displays of kind of what was going on. One vendor had 6 gigabits per second in the downstream on the DOCSIS 3.1 setup, so that was pretty neat to see.
So wait. You said 6 megabits per second.
6 gigabits per second. So they had multiple 192 megahertz channels in the downstream. It's the big vendor that's doing this. Yeah. So 6 gigabits per second in the downstream is pretty awesome.
I think we estimate, even with 1024 QAM, 192 megahertz, we could probably get 1.5 gig. So that must have been about 4 blocks. Yeah,
I think they had 4. I think they had 4 blocks of 192 megahertz. Yeah, that's correct.
Nice.
So, but I mean, it's just definitely demonstrating what you can do with DOCSIS 3.1 on a downstream.
Yes.
And getting that out. So Daniel Howard of the SCTE was there. He chaired one of the afternoon general, or he chaired a couple general sessions. One of the ones that I attended, the SCTE was sort of introducing what they're calling the ISBE, the International Society of Broadband Experts. And I really like the concept behind this because it's sort of a global SCTE where they're bringing together the European and American, all the operational, all of us tech guys and management guys and stuff like that are normally just falling under the American SCTE, but also integrating a European aspect of it, so that now we can ideally start collaborating more and taking advantage of the training the SCTE has, participating in the SCTE list and sort of falling under all one roof. So it's called the ISBE, International Society of Broadband Experts. So that was nice to hear about, and I think we'll get a lot more collaboration with our international colleagues. Also during the general session, it was interesting to hear a lot of the talk from the different cable operators, different large MSOs in Europe, talking about end-to-end operations and how they really need to start focusing more proactively on their networks rather than reactively. And this was really timely because myself, Alberto Campos, and a couple of others were having one of the first presentation at Angacom on proactive network maintenance. So it was perfect. There was a lot of interest in it, and this was sort of the lead in there. And now next year we'll be going back and having a follow-up presentation on proactive network maintenance. So we were also doing demos there. So
did you find a lot of European companies, cable companies, MSOs, if you will, are not using PNM? Are you not seeing it very active, or people not really utilizing it?
So we've been doing some work with PNM, just like trials with a couple, well, specifically one European operator. I know of another cable operator that they're familiar with Cable Labs and their best practices on proactive network maintenance. And what they've done is sort of some command line development around PNM, but anything close to like what we're doing with Nimble This, or what Comcast has done with their Scout Flux system in PNM. I don't think that the work that Cable Labs has done and the work that the rest of us have done to really communicate what PNM is capable of has gone into the European cable operators. So that now sort of what we're doing is trying to make that a push over there. Alberto Campos is working on that. We're working on that. So it's pretty exciting.
We need to evangelize a little bit more. Yep,
absolutely. And that's, so it's starting to happen at this point. Another thing that came out in the panel was I think the same thing that we're talking about here, where Wi-Fi in the home is just an absolute dark spot. And for the European guys, that's their single biggest generator of CSR calls. So they have a really big focus right now on the customer quality of experience, and they're struggling, I think, just like we are, on how to deal with the Wi-Fi connected home. So big problem for them. They do have a heavy focus on DOCSIS 3.1, but what the European operators are doing right now is preparing the plant for DOCSIS 3.1. And they said more so than worrying about buying DOCSIS 3.1 equipment, they want to make sure that their plant is ready for buying DOCSIS 3.1 equipment a couple of years down the road. So they're
in regards to splits, or
So they're looking at changing the splits. They're looking at increasing their downstreams to 1.2 gig. They're also looking at tightening up where their modem performance is, modem transmit power, modem receive power. And so I think their objective is that when they do buy that DOCSIS 3.1 CMTS, not this year, maybe not next year, but in 2 years, and put it in place, that they can take full advantage of it. And that seems to be a big focus of where they're at right now.
Yeah, so the way I see it is, 3.1 definitely gives me more bang for my buck if you can run higher modulation schemes.
Yeah.
And like we've talked about before, we feel that if you're running 256 QAM in the downstream today, you could probably run 1024 QAM downstream, no problem, because of the added robustness of what 3.1 brings to the table. But to really get 4096 QAM, to make it even more speed, if you will, you're probably going to lose 4 or 5 dB of robustness. So if I can get my node +5 down to node +2, node +1, node +0, maybe node +1, it depends on geographics and demographics and geography, whatever. We could probably run higher modulation schemes and achieve much higher speed than what we're getting today, right? Like you said, the customer showed, or at Anga, they showed 4 192 megahertz blocks of OFDM, probably 1024 QAM, showing 6 gig. I mean, that's pretty impressive. It takes a lot of spectrum, but it's, pretty impressive. Yeah. I can foresee the upstream, we always say, is a bottleneck, and I'm interested to see what Europe does with their splits. They're already 5 to 65 in a lot of places, right?
Yeah, so we have. I mean, the obvious easy one is 85, but there are some operators that are looking at 200 megahertz for the split.
I think there's the other split is what, a 204, 250 split or something like that.
Yeah.
Somewhere around there. So I heard a few looking at like a mid 100, like 110 or 117 or some weird split like that. I have a feeling people that aren't familiar with the spec, because it is brand new, they think the upstream has to be like 96 megahertz block, and it doesn't, you know. So if some people are going into this thinking they need 96 megahertz, or well, if I start at 5, I have to go to at least 100,
right?
You know, 101 or whatever. You know, in the U.S., we feel that the higher split is going to be difficult because of millions of legacy set-top boxes. They still have downstream control channel, you know, signaling. And unless I can get rid of all those set-top boxes, I'm kind of relegated to maybe an 85, 102 split.
Yeah, to some extent, you're going to have some cost efficiencies around what the equipment vendors have, because if you're asking for a specialized split in your diplex filter, that's going to drive up the cost. Whereas if you go for something that's readily available, you should be able to get a little better price on that.
It'd be nice if the diplex filters were like FPGAs.
Yeah, they were dynamically programmable. Yeah,
exactly.
I mean, I did a lot of work on diplex filters, and I think it'd be really complicated to come up with a programmable diplex filter. They're a mess.
The hybrids, you could build the hybrids no problem, right? I mean, the hybrids in the upstream could be for 200 megahertz.
Yes.
And it's just a diplex filter and a low pass filter you have to worry about.
Yeah, and the challenge with the diplex filters is that crossover point. It has to be tuned, and I mean, we used to hand tune them. I think they've gotten away from that to where they're all printed on a circuit board, but it's still it's not adjustable.
Yeah.
So on to I think the more interesting part of, you know, how are operators improving their plant, and this goes hand in hand with a number of questions that I've been getting in about, you know, why do we need to have modem transmit powers between 40 to 50 dBmV? What's the benefit of that? Why do you have a lower end? Why do you have an upper end? And how do you do this? You know, what people are talking about using upstream attenuators, you know, devices that attenuate just in the upstream but not in the downstream. Are those good or bad? Where do you put them? Do you put them at the cable modem? Do you put them at the tap? And are there issues with using those? So I've gotten questions about these because there's just a lot of confusion about that. And I thought it might be good to spend just a little bit of time talking about, you know, why we want these transmit powers in the upstream. And even we can talk maybe a little bit about downstream power levels. It's kind of simple stuff, but I still think there's a lot of confusion for people into why we would want a minimum upstream transmit power from a cable modem of 40 dBmV and not to go higher than 50 dBmV. So I thought maybe we could start with that and just talk about basic carrier to noise ratio, signal to noise ratio, MER, and maybe let you take a first stab at that.
Okay, let's start with downstream because it should be the simpler one. We know what the spec says. The spec says the modem should see between -15 and +15 dBmV for the DOCSIS channel it's tuning to. But there's more than just one DOCSIS channel feeding that modem, the front end of the modem. You have analog channels, you have switch digital video, you have standard definition video, high definition video, whatever. You have hundreds of channels slamming into the front of your modem, which could cause distortions in the modem itself. So there's another spec a lot of people don't know about. It's a total power spec into the modem. So if you look at a typical RF plant, you're coming out tilted from the amplifier. Depending on where your DOCSIS channel is located in that spectrum, if the DOCSIS channel happens to be in the low end of the spectrum, well, that means your analog channels are 6 dB higher plus the tilt. So that power from all analog channels is probably much higher than what you think or what it really needs to be. But then if you go to the last tap, you're probably negative tilted. And now if your DOCSIS channel happens to be at, say, 600 megahertz, your analog channels at channel 2, 3, 4, 5, 6 are probably much higher, maybe 10 dB higher than, maybe 15 dB higher than your DOCSIS channel. You know, the 6 dB of delta between digital and analog, and then the tilt that comes into play. So what we would like to see is modems getting hit between -5, +5. If you're between -5, +5 at the DOCSIS channel, then all your other channels are probably within reason and not going to overload the 30, what is it, 30 dBmb total power or 35?
It's for total power. Actually, I think it's like 31 was in the DOCSIS 3 spec. 31, 32. Okay. But it's around that total power.
It's like, let's not squabble over a dB. It's like, why did they add a dB, right?
It's a dB amongst friends.
Yeah, no kidding. So whatever. So I usually try to shoot between -5, +5. I know I'm happy on my downstream. But I have seen modems hit with -15 and still work. I've seen modems get hit with high level, and you think that'd be better? It's actually worse. When I get hit with too high of a level, I know all my other channels are going to overload it, and I sometimes see worse MER. I don't know if it's intermixing, causing distortions, noise, intermodulation noise inside the modem itself. So -5, +5, perfect. My modem should be able to read MERs of like 40-some dB, which they seem much better than they used to be. If we try to quantify those MERs in a downstream, we could probably feed that back and get a good idea of what we could run for DOCSIS 3.1. I know from the beginning with 3.1, we're looking at 4 mod profiles. A robust profile, probably 256 QAM, a less robust but more speed, maybe 1024, maybe a 4096 QAM, maybe a mix. And then you could take all those modems, whether it's an SDN app, SDN stands for
software defined
network.
Networking, yes.
Yeah.
I believe.
Yeah.
Yeah,
no kidding. That's why I didn't blur it out, because I wasn't exactly sure of what it really is. Software defined networks. You can write an application that could poll the modems for their downstream MER, and then you could say, all right, these modems have an MER that's pretty stable. It's in this window, and I could give him this mod profile while I give my neighbor a different mod profile.
Yeah, so I think the point you're bringing up is really good. We've got if you do that, if you run that poll and you say how many modems are running at or above 39 dB MER in a downstream, you're actually going to see a lot in most cable plants. And I think the magic number to be able to support 4096 QAM in a downstream with LDPC is 39 dB. You might check me on that. It's like 1 dB or so, but it's
you need to get Ron on this call.
Yeah, but it's like that's the magic number, and so a lot of modems already support that. But you will find there's going to be a certain percentage of modems that are going to be below 39 dB, and if this goes on to you're going to have multiple profiles. But so sort of why we're talking about this is those modems that are less than 39 dB MER, maybe their transmit power's too high, or maybe their transmit power into them's too low, and now's when we want to start looking at that. And one of the analogies I like, I just want to touch back on your too much transmit power into a modem. It's kind of like a stereo and speakers. You know, you can have small speakers and a big stereo. And the speakers can sound, the music can sound really good coming out of those small speakers until you turn your stereo up really, really loud. And now you're putting too much energy into those small speakers, and they start to distort. And then that's the same concept with putting too much RF energy into a cable modem. When there's too much RF energy going in at the cable modem's not going to get the signal it's going to distort, and that MER is going to go down. So that's a good case where, you know, too much energy into the speakers is going to sound bad. Too much RF energy into the cable modem is going to make the MER worse.
Yeah. So it's interesting. We talk about the MER at the modem, and we're all using this term generically. It's like MER of what? I could have 4,000 to 8,000 subcarriers in a DOCSIS 3.1 192 megahertz block. I need to get an MER of every single subcarrier potentially, or maybe the MER of all the pilots that happen to be thrown in there in that 192 megahertz. But it's, you know as well as I do, we've been dealing with RF plant for a long time. The spectrum's not going to be the same everywhere. You know, for one house, the spectrum could have a suck out at one frequency. It could have a hump at another frequency. It could have noise popping up in one frequency. It could have roll off at the high end. So that house, I could feed back an MER, but is that MER realistic for the whole spectrum that modem is using? No. So I need to then say, all right, I got an MER, but And here's where I think it's going to get more complicated in the future, because we're not going to be able to give everybody different mod profiles on the downstream. Meaning, we might come up with, say, 4 basic mod profiles to begin with, but let's suppose the modem reports 40 dB MER for one channel, because I was only doing DOCSIS 2.0. So it reports 40 dB MER. I'm like, oh, he's a good candidate for DOCSIS 3.1, and I'll do 4096. Well, yeah, you could at that one frequency, 6 megahertz wide, but did you really quantify or qualify 192 megahertz of his spectrum? Like, so what is that modem going to do if he does? And here's where it's complicated for me too. It's going to be a conundrum, I think. How much processing are we really going to do for every single modem at every single subcarrier? Do we say, all right, this modem has a 40 dB MER, but in the whole spectrum, his lowest subcarrier was a 28. In that case, what do? Do you force that modem to 256 QAM across the whole board, or do you just null out some of the subcarriers at the modem?
I say just null them out, because you're just making this all really complicated on my brain.
I know.
I mean, I was thinking the modem, it's 42 dB. DOCSIS 3.1 is going to be awesome, and now you're making it complicated on me, man. This is terrible.
And that's what I mean. It is complicated, right? I mean, it's a lot more spectrum, and I'm a realist.
Yeah. Thanks, man. This was a good Friday up until now.
I think you're right, though. I think you would have to look at all the MERs of the subcarriers of the modem and say he's a good candidate if he has a good MER on all the subcarriers, or I notch some of the spectrum out just for that modem somehow.
Yeah. So one of the cool things about with a DOCSIS 3.1 CMTS and cable modem, part of the one of the PNM hooks is you will actually be able to get, whether you want it or not, the MER of every subcarrier. It's a tremendous amount of data. If you've got 8,000 subcarriers, you're going to have MER on 8,000 subcarriers, but it's going to be there.
And that was just one block. If we had 4 blocks of OFDM, now we have what, 32,000 subcarriers?
Yeah, that's pretty big.
Potentially, yeah. So I get your point. So on the downstream, I think understanding that most of our problems, downstream is not so bad, right? Everything's broadcast out. The 3 ingress sources I see as potential issues are problems on the downstream are in the head end, where edge QAM or something goes down, but that affects everybody. The other one will be off-air ingress. That could be LTE, or could be off-air digital broadcasters. But when that ingress gets in, it only affects everyone downstream of the ingress source, right? Mm-hmm. And it's always at a specific frequency. So any modem that sees that problem will report back to the CMTS, a CM status message, and say, we're all seeing the same issue, so put us in maybe a resilient bonding group, a dynamic bonding group, a partial mode. So having more downstreams gives me and affords me more redundancy for the modem itself, assuming I don't lose its primary. If I lose its primary, I have to reset anyway. But if I only lose secondary channels, it can go to partial mode and then come out of partial mode. So it gives me a little bit more resiliency when I have more channels that the modem is bonding on. But the third problem I'm seeing with downstream resiliency would be at the house. Individual household problems like suck outs, roll offs, things like that, where it's totally different from my house to my neighbor's house. Now the CMTS has to make a decision. Do I make a bonding group for you, and one for you, and one for you, and one for you? So you could be doing 7-channel bonding. I'm doing 7-channel bonding, but different 7 channels, because I had a different RF frequency response than you did. So, I mean, those features are good. And I bring this up because you were talking about we need to get better at monitoring what's going on in our plant and quality of our subscribers. I have subscribers that think they're paid for 8x4 modem, 8 downstream, 4 upstream. The CMTS might be partial mode. That mode, or it could be partial mode and it didn't drop to a sub bonding group like 7 channels, it dropped to single channel.
DOCSIS 2.0 mode.
Yeah. And so how do I know that customer's paying for 100 megabits per second isn't getting 20, and that's the whole problem, is he's not getting the pipe that he paid for. Right. So we need to be proactive to monitor the CMTS and service flows and and maybe even utilize the FTP server in the modems, the newer modems, and do a speed test without the customer even knowing I'm doing it.
Yeah. Also, that's a feature in DOCSIS 3.1 where you can, which I'm sure you know, you can do speed tests in the background between the cable modem and the CMTS without the customer knowing that that's going on. So, really,
yeah, it's actually in. I know Broadcom, I think, implemented in some of their newer chipsets, the 3.0 chipsets.
Yeah.
So
Yeah. Well, they're anticipating the 3.1 stuff coming out, so they're putting a lot of cool features in. I want to take a couple of minutes here. We have a couple questions coming in. I'm getting behind on. So the first one was actually just a comment from Sean Ollerton. He says this was back on our PNM discussion about the European side. He's absolutely right about this comment. He says he thinks that the PNM part is recognized, but still being tested and evaluated in Europe. So it really needs to focus to get this going over there. So he was just making a comment on that. And then Sean also had a question when we were having the sort of 3.1 discussion. He says, to get these figures, will the head-end setup have to change, i.e. Cisco 3.1 and Aris E6000 UBRs to eliminate the RPM and FPMs presently in them? So RPM and FPM.
Is that the path
I think it's return path module and forward path module. So I wonder if he's talking about is it the speed or the MERs?
And what was the first part of that question?
To get these figures, will the head-end setup have to change, i.e. Cisco 3.1 and Aris E6000 UBRs to eliminate the RPM and FPMs presently in them? So
I'm confused by that one.
Yeah, Sean, if you can just send a follow-up question in, we'll take a look at that. We're not sure what figures you're looking at here. If you're looking at throughput speed, or if you're looking at sort of MER, or if you're looking at reading maybe MER per subcarrier. So please ask a follow-up question, clarify. Thanks.
So we hit the downstream stuff. Upstream, as you said, 40 to 50 dBmV, perfect. You know, I usually say if you plot out modem transmit levels on the upstream, you'd have a bell curve, right? A bell curve of transmit levels. A lot of people have a bell curve that's really kind of rolls. It doesn't
20
off,
dBmV,
it rolls off. Yeah,
to 55 dBmV. It's all over the place.
Yeah, I mean, typically I'll see 35 to 55. But you will have some that's on the low end, like it could be 25, and it turns out to be a modem in the head end that they're not installing proper padding to make it transmit hotter.
Yeah, so I think
they just find pickoff points.
I think one of the first questions that people have is, what does it matter if my modem's transmitting at 25 or 30 dBmV? How does increasing the transmit power help the modem, help the subscriber? What's it matter?
All right. So let's show the bell curve like this. On the high side, my right hand, your left side. On the high side, to drop it down, if you don't drop it down, modems go offline because they have max transmit power. Then after a certain window on the CMTS, like, well, you're outside this window, so I'm not going to do station maintenance anymore. So you're going to get a downstream sync loss. You're going to T4 timeout. You'll rescan downstream. Let's try again on a different upstream, maybe.
Sure. And when you start channel bonding, it's easier to get the max transmit power, because if you're doing, say, for channel bonding in the upstream, your max transmit power is like 52.2 dBmV per modem, right?
It's 51 dBmV
51.
per channel.
Now here we go. Back and forth on a dB.
Per channel, but if you're using 64 QAM.
Okay.
So you gain a dB if it's 16 QAM, and then you gain 3 dB if it's QPSK.
Yeah.
So it's 51 dBmV. Now, so if your modem's already transmitting 54 dBmV with DOCSIS 2.0, and then you try to do 4-channel bonding at 64 QAM, it may work depending on the CMTS, or it may not. And it may work and register, but when it gets really hot out, it might go offline. Because when it gets hot out, there's more attenuation.
Sure.
And most amplifiers don't have reverse thermal EQs.
So this is why we want to keep that transmit power 50 dBmV or less.
What I'm hearing lately is, try to design for like 48 because that gives you 3 dB of headroom to 51.
Oh, 48.
I know,
Now we're really pushing.
Yeah, I know. Exactly. I agree. So get this. I have an 8-channel upstream bonded modem, and you would think with the 8-channel upstream bonded modem, they would have implemented the Cable Labs ECR that says, here's the extended transmit power.
But they
plugged it in. Yeah, they didn't. They dropped another 3 dB. It's 48 dBmV max power. So I did 8 channels of upstream bonding at 64 QAM, and the max output was 48. I'm like, wow.
Yeah, so now the recommendation drops from 48 to 45.
Yeah, that's bad. We're changing taps now and all kinds of stuff. So there are a lot of ways to get this bell curve to be tighter. And if I could make it tighter, I would shift it up probably close to 45. Because then it would be maybe a 50 to 40 window with centered at 45.
Yeah.
Exactly where you started, right? But our bell curve is wide, low, the tail ends are like sliding off.
So I think people can understand max transmit power. We can understand why the modem's going to go offline. But why does it matter if the modem's at 25?
Let me get to the other part. So we bring this end in by making modems not transmit too hot. Now, how do we do that? We use, they're usually too hot off a high value tap. So you drop your 26 tap off the amplifier to a 23 tap, which is what a lot of people did in the early days. You change the taps into like a cable simulated tap. They're making those now, where the tap itself could be 32 dB of loss at 1 gig. It sounds like more, but that's at 1 gig. And at 5 megahertz, it might only be 17 or 20 dB of loss. So the upstream frequencies that come from that house is seeing much less tap loss. Because right now they're seeing 23 dB of tap loss, maybe 26. If you can make that look like 17 or 20, you just gain 3 dB for that house. You understand? Makes sense, right?
Sure,
so
absolutely.
That's one way to pull that in. The other way would be take the whole bell curve and shift the whole thing down, but now it's even worse for everybody. If you keep shifting this whole bell curve down, modems will transmit lower, the MER for everybody gets worse. So running a higher MER or a higher power level usually has better MER. But what about the modems that on the low end of the bell curve, they're transmitting 35 dBmV? As they go through the plant, they still hit the CMTS at 0. Everybody has the same noise floor. In theory, they should, right? Because all the noise funnels back. So everyone's hitting the CMTS at 0. The noise floor is the same for everybody. Now, what people don't understand is, why do I want a modem to transmit hotter? What's wrong with 35 dBmV? So the first thought is, if you run the modem lower output, its own noise figure will be bad. I've never seen that as a problem at all. I've never seen that. Back in the day when we both worked at C-Core Electronics, we would think about running up converters really hot and then just padding down externally because that would get a better MER right from the up converter.
Yep.
We're way past 20 years ago.
I feel that. I feel
So that is not the problem. The noise figure of the modem is not the problem. You can run it low and still have great MER coming out of the modem itself. The problem here is if the modem sees low attenuation to hit the CMTS at 0, it's only transmitting 35. That means any noise from that house also sees low attenuation. So what we know is most of the noise floor in the head end is attributed to the low value taps. Most of them are coming from the 11, 8, and 4 dB taps. We need to make those taps look like higher value taps so that the noise that comes from those houses sees almost the same attenuation as noise that comes from a 26 dB tap.
So what you're saying is it would be better if those low value taps had more attenuation
on the low frequency. Yes.
Right at the tap, not inside.
We would call it a step attenuator. Like we had those ideas of step attenuators, and I had the idea, and I called up when I was at C-Core a long time ago, and I called up Eagle Comtronics, and I said, I want a filter, but I want the filter to not notch out 30 dB. I want the filter to notch out 6 dB. They're like, oh, we just came out with that. It's called a step attenuator. I'm like, damn it, there goes my patent. Because I was thinking, all it is a filter, but instead of notching down 30 dB, because I wanted a high pass filter, I wanted to cut off at 42, whatever, but only notch down 6 dB. Basically, you created a 6 dB pad only on the upstream frequency. And that's what they came out with, called step attenuators, meaning 6, 9, 12. You could screw it right on to the tap spigot. And that basically, the downstream looks fine, maybe a dB of loss or half a dB of loss. And the upstream happened to see 6 dB more loss. So that 4 dB tap looked like 10 dB of loss in the upstream.
Right.
But then you might say, well, if I just want to make the modem transmit hotter, can I put the step attenuator on the modem? I'm like, you're not seeing the forest through the trees.
Because you're not achieving what you said you wanted to do by putting that attenuator at the tap. You're making that tap look like a higher value tap and reducing
and why the tap? Because we know most of the noise that gets into the plant is between the tap and the house, right? Well, not the house, but the tap and inside the house. We always say that 5% from the plant, 20% for maybe the drop line, and 75% for the house.
Right.
So the step attenuator would do good at the ground block, but it's probably easier for me to control as a technician to put it at the tap anyway. You don't want to go into easements and go into the back of the people's houses and stuff like that, and then people messing with it, right? So you would put it at the tap. But now these step attenuators, like, you're going to put one and everything will drop. Why not just buy a tap that has it built in? So you could do that. The taps have equalizers now, not just a step attenuator, but maybe an equalizer in the tap. Now, I like the idea of an equalizer 5 to 1 gig or 5 to 1.2 gig, because instead of making the tap, say, a 4 dB tap for end-of-line tap, you would make it 4 dB at 1.2 gig, but you would make it maybe 11 dB or 13 dB at 5 megahertz. You equalize the tap. Because think about the downstream also. As you go through coax, your downstream does this at the last value tap. So instead of putting a field equalizer in your plant, in the tap itself, you put an equalizer.
Right. So because you end up with negative tilts when you start to get into the house. Exactly. You're saying that equalizer will give you flat. It'll compensate for that negative tilt, and now you're getting 2 for 1. You're compensating for the noise. You're getting better upstream carrier to noise ratio, better upstream SNR.
Downstreams are better.
Flat into the house, flat signal into the house.
Yeah, the downstream is flattened out. The other reason I like the idea of an equalizer pivoting at 5 megahertz, or pivoting at 1.2 gig, whatever, is if you buy something that has a filter in it and a step attenuator, what do you do later if you change your diplex filter splits? You got to change every one of those.
Yeah, that's a problem. That is a big problem, actually. So
and we all know filters create group delay.
So that was one of the questions that also came up. Is there any problem of buying these step attenuators? And I think you just touched on it. If you put a bunch of step attenuators that have a cutoff at, say, 42 megahertz, and now a year from now you go out and you change your plant, say 5 to 85, 5 to 200 megahertz. You have a bunch of step attenuators that are stopping at 42 megahertz. So that would be a reason to maybe not use step attenuators and do what you're suggesting is use a cable simulator or an equalizer that has a nice flat response from 5 megahertz to a gigahertz, or even ideally 1.2 gigahertz to future-proof your plant, so that you don't have to go back and replace all those step attenuators. You've got a more future-proof system.
Yeah, you're not creating a filter that has roll-off, that has group delay. Yep. You're not hamstringing yourself, for future expansion. So it all comes down to money. So it's going to cost more money to do upgrades and tap changeouts, stuff like that. If it were my system, and I was worried about cost, which I would be, of course, to bring the low side of the bell curve in and make the modems transmit hotter, and in turn drop the noise from those low value taps, I would probably, in my design, I know the walkout and the maps aren't exactly the same, so it has to be designed and tested. But in the field equalizer, a lot of times when you have long coax runs, that's where you have this disparities because of long coax runs. You have usually an inline equalizer. And then in that inline equalizer, I would make it not a filtered inline equalizer. It wouldn't just hit downstream. I would still do this idea of equalizing from 5 to 1.2 gig. That's one for the entire branch. So I'm not changing out the taps, because that could be, that one leg could branch off to 2, 4, 6, 8, 10, 12 taps. you know, 11 and 8 and a 4, and then it breaks off to another 11, 8 and a 4, and it breaks off to another 11, 8 and a 4. So that one field equalizer could potentially hit 30 houses, right? I mean, it depends on demographics, obviously.
Yeah, of course.
You get the idea.
Yeah, yeah, and like you said, you future-proof yourself ideally a bit, because it may do better.
You may, and we've seen this where people have done stuff like this, and the whole noise floor for everybody, because that noise all funnels back to the CMTS upstream port, the whole noise floor dropped like 9 dB. I'm sure it's going to be dependent on, you know, how bad the noise is out everywhere, but that actually helps create a lower noise floor, which in turn might allow me to run higher modulation streams for DOCSIS 3.1 in the upstream.
Yep.
Maybe 1024, you know, 1024 QAM in the upstream.
Okay, good. Well, I think we've pretty well covered this downstream into the cable modems, upstream into cable modems, how that's going to help improve performance, and ideally, if you're doing this now, you're going to have better downstream MER into the cable modem, better upstream SNR into your CMTSs, and then you're going to get better performance today, and then prepare yourself for DOCSIS 3.1. Sean did respond back with some clarification onto his question, so I'd like to cover this and see if we can give him an answer. So he talked about RPM and FPM, and he gave us some definitions on that. The RPM combines RF before the optical transmitter, and I think he said that was like return path matrix. The FPM combines and amplifies the RF, VOD, video on demand, broadcast modem channels. The RPM amplifies the RF out of the optical receiver. So he says the newer UBRs can do this, eliminating the need, or he's asking, can the newer UBRs do this, thus eliminating the need for these?
CCAP. It sounds like CCAP. It's like saying, yeah, can the newer CMTSs do video and DOCSIS out of the same port, which is yes.
Okay.
All right. Because it sounds like he's just talking about, you know, running your best effort data and your video, and then having to do external splitting, combining, and then, you know, then split it to broadcast it down all your plants or whatever the service group sizes are. We can do that now with any CCAP box, you know, the converged cable access platforms, whatever.
So you stick to CBR8 or?
Yeah, the CBR8, even the 10K with the RF Gateway 10 has the capability to do video on that as well. So I don't know if that's sort of where he's going with this. And that was the whole premise behind CCAP, was to eliminate some of this equipment, the splitting, combining, the cabling. The only bad thing is once you put all your QAMs down one connector, your service areas have to be the same.
Right.
Meaning, if I want to run DOCSIS to one fiber node, but my video would typically run to 2 fiber nodes, how do you do that if everything's coming out of a single connector? Now you have to take that connector, and if you split that connector, now you're running DOCSIS to 2 nodes because the DOCSIS is on that connector.
Sure. Yeah.
Yeah. Yeah. So you turn out having to do your service group overlays, or you have to figure out how you're going to narrowcast versus broadcast versus multicast and things like that.
Okay.
Hey, I had a question for you. Was there a lot of talk about remote PHY architectures at ANGA?
You know, actually, there was remote PHY at ANGA this year, and remote PHY has been there. I would say, you know, well, CMTS in the node. I wouldn't say it was more prevalent, or it was any more prevalent this year than it has been in the past 2 years. Because I would say the past 2 years, we saw remote PHY, we saw CMTS in the node before I think we even saw it here in the States at Cable Tech Expo. I almost think it was maybe a little less in your face, where, you know, this year it was more DOCSIS 3.1 was the big thing that everyone was talking about, and oh yes, remote PHY and CMTSs in a node we've been talking about that for the past 2 years, so it was not new this year at Angacom. So.
It's interesting, you know, what we've been talking about is running different modem levels, trying to get better MER, but a lot of our Achilles heel happens to be the optical link.
Yes.
So unless we drop our analog links and go to digital, and whether that digital is baseband digital, which would be remote PHY, or it's baseband digital reverse, or, you know, which kind of digitizing the signal, but it's still an analog plant, if you will. So I know some people are looking at stuff like that, like Aurora's systems would be sort of like a digital type of link. I have a lot of people doing baseband digital reverse on the Upstream, which usually gets better MER readings. It's still a DFB laser, right? Usually it's DFB laser. But I mean, if people are looking to upgrade their fiber nodes, they should look at the fiber nodes that can be upgraded to 1.2 gigahertz right from the get-go, and then maybe remote PHY capable as well. So if I'm going to do a plant build out in the next couple of years, I'm going to look at, what does remote PHY bring to the table? The remote PHY is just for the DOCSIS part. You still have to have video somehow.
Yeah.
So you might still have 1550 nanometer light feeding an optical link for downstream, and then upstream, maybe it is all DOCSIS on the upstream, or maybe there's some type of out of band signaling or fiber or optical link or whatever. But these are the discussions that need to be made, I think, for the next few years when people are looking to build out. Do I do 5 to 85 megahertz now? If I do 5 to 85 megahertz, is it a simple diplex filter change out? Maybe I can do it in the field without having to do bench sweeping. If I do the step attenuators or equalizing tilted taps, are they a built-in filter that I might have to change out, or are they, from the whole spectrum? So I think that all those concerns are still coming up, because you were talking about DOCSIS 3.1 and building out the plant or cleaning up the plant to support it. But I see 3.1's beauty of higher modulation schemes with remote PHY, more achievable than what we have today.
Completely agree with you. And I think anyone who's spent any time in the field dealing with laser clipping and problems inherent with analog optics would agree with you that if you want to really take full advantage and get a lot higher data speeds in a return, you absolutely have to eliminate the analog optics and go to some type of remote PHY architecture to just get rid of that, whether it's digitizing the return or demodulating the return at the edge at the fiber node. So completely agree.
I agree.
So, all right, sir. Episode 13 is in the can. Happy Friday. Thanks everyone for tuning in, and have a great weekend. Bye.
All right, take care.